So now what we're going to talk about is we're going to talk about something called curl. And curl is another way of classifying or characterizing characteristics of vector fields, a lot like divergence. The difference, though, with curl is that curl is going to actually give us a vector value. So what curl is going to do is it's kind of going to like determine the amount of what we call spin of the vector field at a particular point. Like, how spinny is it? All right, I guess that would be the best way to think about it. Is there a lot of rotation? All right, so you imagine you kind of like you have like a sinkhole or something like that. You have a lot of rotation, or like something that kind of flows around like a toilet bowl, that kind of thing. Is there none? Right, like we don't have any rotation whatsoever. We got kind of something that's perfectly flat, and so you can imagine that if there's no spin, we'd end up having like curl of the zero vector. Okay, we'd have the curl of the zero vector. Basically, there's no curl whatsoever. On the other hand, we could imagine something that has like a lot of curl, and we'd have a vector that has a really large magnitude, all right, and maybe is moving in a particular direction, okay? What that actually brings us to is it actually brings us to a really important point, and we're going to talk about that in just a second, is that curl is not a scalar function like divergence. So we're not going to get a scalar back for curl. Instead, what we're going to get is we're going to get a vector, all right? We're going to get a vector, and that's going to tell us a direction, okay, and it will also have a magnitude. So talking about the concept of curl, the curl of a vector field at a particular point, right, is going to be that spin and its direction of the flow of the fluid in the vector. Curl, however, again, like we said, is not going to be a scalar function. It's going to end up being a vector function. And when we actually look at it, you'll see. So let's imagine that we have something like this vector field that we saw before when we were talking about divergence. And what you can kind of see is that if we kind of imagine in this region right over here, you can see that there's quite a lot of spin. Pick a particular point, and you can actually see that there's kind of that spin. It's spinning in a particular direction, okay? If we choose a different area, you can see that there might be, a smaller amount of spin, right? Like in that area there, because we've got smaller vectors that are kind of moving in and out, okay? And so consequently, you can characterize in terms of, and when we talk about spin, let me kind of just see how, if I kind of draw these lines, I draw lines around my vectors, you can see the kind of the curving. That's what we're talking about when we talk about spin. If I look over here, we've got very small vectors, right? There is some curve, like there is a little bit there, but it's not quite as much as it is in the outer one. Looking at a different one, we look at this one here, and what you've got is you've really got here, you've got nothing, okay? You've really got no curve, right? Everything's kind of moving inward, right? So like if we were here at, say for example, at the origin, right? Everything's moving in towards the origin. There's not really any spin that's going on inside of that particular vector field, or at that particular point. If we come up over here, pretty much the same thing. Everything's either moving in or moving out, right? There's no rotation that's happening there inside of this vector field, and so consequently, we don't really expect that there is any curve at all there, or curl at all there. If we're going to define curl, we're going to let F be our vector field, PQR, and it's in R3. We can also imagine this in R2 as well. And we've got Px, Qy, and Rz all exist. Then the curl of F is going to be defined as Ry minus Qzi plus Pz minus Rxj plus Qx minus Pyk. So that's going to be with delta R dy minus delta Q dz I plus the partial of P with respect to Z minus the partial of R with respect to X, J, plus the partial of Q with respect to X minus the partial of P with respect to Y, K. Now what you'll actually notice is that we can kind of think about this in these terms. We actually saw something like this for, you'll see something like this for divergence. If we rewrite this, I've got I, J, K, okay? And I'm going to have del X, del Y, del Z, and this P, Q, and R. What you'll notice is that this equation right here is going to end up being equal to the cross product of this thing here. If you were to, now, okay, so it's important to get that this is a conceptualization, okay? We don't technically take the derivative of Q with respect to X here and take the derivative of Y with respect to P when we go out and take the cross product. But you can kind of imagine that that's what's happening. So we'd actually kind of call this, right, the gradient, because that's what this is, that's the gradient, okay, cross our vector field F. And that's another way that we notate sometimes the curl of F. I'm not really a huge fan of that. I mean, I get it. You know, it's a good way to remember how to find it, I guess. But it strictly isn't actually true, because you're not, in fact, multiplying here, you're actually taking derivatives. But you will see this thing here written as del cross F. Just like you'll see the divergence written as del dot F, even though that also is. Let's go find the curl of F at 0, pi over 2, pi over 2 for F equal to sine x cosine z, sine y sine z, cosine x cosine y. So we've got P is going to equal sine x cosine z. Q is going to equal sine y sine z. And R is going to equal cosine x cosine y. What I'm going to need to do now is I'm going to need to find the partials of each one of them. So I'm going to find P of x, or excuse me, not P of x, but I'm going to need Py and Pz. Okay, I'm going to need Q, Qx and Qz, and I'm going to need Rx and Ry. Okay, so notice that this is like our z component, this is our y component, and this is our x component. And what we're going to do is we're basically going to find the partials with respect to the other variables. Okay, the other variables for each one of our functions, or each part of our vector field functions. So Py, if we look at Py is actually going to end up equaling 0, because there's no y value in there. Pz is then going to equal negative sine x sine z. Qx is going to equal 0. And Qz is then going to equal sine y cosine z. Rx is going to equal negative sine x cosine y. And Ry is going to equal negative cosine x sine y. So those are our partials. Now what I'm going to do is for my I, j, and k, okay, my I, j, and k, I is going to be del r del y minus del q dz. And so if I go over here, del r del y, that's going to end up being negative cosine x sine y minus, and sine y cosine z, I, that'll be our ith term. We're going to add to that now the p dz minus dr dx. And that'll be our jth term. So our p dz is negative sine x sine z minus, and then this is dr dx is going to be negative sine x cosine y. All that's going to be our jth term. And then finally our kth term is going to end up being dq dz minus dp dy, or excuse me, dq dx minus dp dy. And that's our kth term. And so that's going to be plus dq dx is 0 minus dp dy is 0, k. And there we go. Now we're going to evaluate that at 0, pi over 2, pi over 2. And so we start here. First term, cosine of 0 is 1. So this is going to be negative 1 times sine of pi over 2 is 1. 1 times 1. Minus, this is going to be sine of pi over 2 minus 1 times cosine of pi over 2 times 0. And that's our ith term. Plus, this is sine x is 0. And so minus, or plus in this case, sine x again, that's a 0 again. So that's our j term, and then plus 0k. So our vector here is going to be negative 1i plus 0j plus 0k. And that is the curl. So now let's find the curl of f. This one's going to be a two-dimensional vector field. So we're going to need actually a slightly different equation, but it's actually a lot easier. Our curl of f in this case is going to end up equaling qx minus pyk. Okay? So essentially what we'll do is we'll take the derivative of q with respect to x, so that's 1, minus the derivative of y, or derivative of p with respect to y, So that's -1. So this is going to be 1 minus a -1, which equals 2. So it ends up being 2k. So the curl of a vector field tells us the amount of spin that we can expect inside of that vector field. Generally, we calculate it at a point, and what we want to notice is that it itself is a vector, right? So it's going to be a vector quantity. Unlike, for example, divergence, which is a scalar quantity. So that pretty much kind of summarizes what we've got for curl.